Hello, everyone. I'm Sinan Güntürk. Welcome to this month's Turkish Math Society Distinguished Colloquium. It's my great pleasure to introduce our speaker today, Professor Ingrid Daubechies, who is the James Duke Distinguished Professor of Mathematics and Electrical and Computer Engineering at Duke University. Ingrid Daubechies needs no introduction, and I cannot do justice to doing it in a short amount of time anyway. Her mathematical and scientific contributions have been recognized numerous times and at the highest levels, the most recent one being the Wolf Prize this year, which you may have heard of. She has been among the foremost applied mathematicians in the world since the 80s, best known for her foundational and transformational work on wavelet theory and its applications in engineering and sciences. But that's only one of the many reasons to know her. Today, we're very excited to hear her talk on machine learning, the old-fashioned style. Ingrid, the floor is yours.
Thank you so much, Sinan. And yes, so as Sinan was already saying, I'm going to tell you about what used to be called machine learning, and it still is, but it doesn't have anything to do with deep neural networks. And the younger ones among you may consider it very old-fashioned, but it still has a lot to teach us. So, well, let me start with some analogies. If you have a surface like this two-dimensional surface embedded in 3D, rendered here, then it's clear, because we can see it very well, that the 3D information of the coordinates of the points will hide the fact that we have really a two-dimensional surface. And in particular, the distances in 3D between points are not the distances that we would like on that blue surface. So we'd like to, when we have data that are lower dimensional in a much higher dimensional setting, to be able to extract from them that lower dimensional geometric structure, even though it's not highly nonlinearly embedded. So diffusion maps are a way to do that. The idea is that if you have all your data points on that surface, then you can imagine knitting it together from local geometry. So we are assuming that our embedded manifold has a Riemannian structure, so that we can, if we have enough points on it, feel that we have a good approximation to the local tangent plane. And we can then use that to knit things together. And that's a little bit. So what we will do is we'll knit together the local geometry. We'll take neighborhoods, and they are like little local disks, if you want, that approximate the local geometry lifted from the manifold to the tangent plane via or from the tangent plane back to the manifold via exponentiation. And so we are going to make that local diffusion using the high dimensional geometry to then define random walks to diffuse, which is the same thing as doing random walks on the manifold. So it's a little bit like having these surfaces approximated by little flat disks that together, because we have the whole collection of them, will give us an idea of the surface. So we can diffuse on each of them, and because they overlap, we can then jump from one to the next, and that will allow us to build a longer diffusion map on the whole surface. So the way you do that mathematically is that you have all your data points, and you have distances between them. The only distances you have are with respect to this higher dimensional manifold in which they're non-linearly embedded. But you can use that to define a heat map, I mean, non-normalized, as you would in all the Euclidean spaces, the diffusion always takes the same form, this e to the minus distance squared over 2 tau, with normalization, of course. We are in problem with our normalization because, yes, we can approximate at small distances as if we were on the tangent plane, and that has the right dimension as opposed to the full dimension. We don't know that dimension. Moreover, our data are sampled very haphazardly, and in some points we might have more neighbors than in others. So one way to get around that and to really have a diffusion map, I mean a map that maps the constant 1, the density 1 everywhere to 1 again, so a stochastic matrix, is to just compute for each point what the weights are from all the neighbors, and use that to normalize our map. So we by computing this diagonal weight matrix and putting the inverse in front of our W tau, we have now a matrix that defines a random walk on the graph. Now, picking tau in here is, of course, something for which we have to be careful, because if we pick tau too small, we need to pick tau not too large, because if tau is very large, then all these W's are going to be too large, and we are going to take into account distances on our base manifold, on our manifold, since we are using the high dimensional manifold to measure these distances that are not appropriate. I mean, remember the blue curved surface, points that were far apart had distances that had nothing to do with the local blue surface. When they were small, yes, not when they're large. So we don't want to pick tau too large. On the other hand, if we pick tau too small, then the matrix is going to have no information about neighbors, because as soon as the distances are non-zero, if we pick tau too small, that ratio will become too large, and all the non-diagonal matrix elements would become negligible. So you want to pick tau large enough that you are really still learning about the local manifold that you want to learn, and but not too large. So in order to, a rule of thumb that we developed, and that's something that was done by my then graduate student Shan, who is now long promoted to academic adulthood and is researcher in Denmark. If we had a true diffusion, then we would have, for the operator that depends on this time parameter, a semi-group property. If you diffuse by time t and diffuse by an extra time s, that is like diffusing over the whole time t plus s. So what we do is we pick tau, we look at the difference between our diffusion matrix squared and the matrix for 2 tau. And if the square is close to the matrix for 2 tau, our tau is a reasonable parameter. And we pick tau as large as we can do it within that criterion. Okay, so we have a way of picking our diffusion time, and now we can look at the spectral decomposition of that matrix. There are some tricks to do that, because the matrix, as you see, is not diagonal, but you can render it by a similarity to a diagonal form, and then you can find its eigenvectors and eigenvalues. And we are looking at very small tau, but once you have a decomposition into eigenvectors and eigenvalues, you can do 2 things. First of all, you can truncate, because we know that the data we have are going to be very noisy. So we expect that beyond a certain label of the eigenvectors, noise will start to dominate. So we can truncate. And the next thing we can do is that in spectral decomposition, we can take a power of the eigenvalues, which is like knitting the little patches together. It is like looking at a higher diffusion time, once we have put in the right structure. And that gives us an embedding to a feature vector, and we can then compute distances in that embedding, that Euclidean distance in that embedding. And that gives reasonable results. And so I'll show you later data on which when we have a way of computing distances, we get for a population of 50 data points where that are really, we have a ground truth. We know that they are constituted by 5 large groups of 10 points that are more closely related. And when you make a multidimensional scaling of those distances, you get the picture on the left. If we then, to that same data set, apply the diffusion picture and use that to get a more geometrically informed representation of the 50 data points, we get the picture on the right, in which you do see that we have a much better clustering of related points which have the same color than we did at first. So this actually was in the case I'm going to the case study I'm going to talk to you about, a very important graph, because it convinced our collaborators that we really knew what we were talking about. So let me tell you, and so the diffusion distance indeed was given by this this formula that I gave you. Let me tell you about that case study. So it all started by a conversation with biologists. So Jukka Jörnvall is a very distinguished morphological anthropologist. These are people, and Daubechies was at that time his postdoc. He's now, by serendipity, he became a professor in the same institution where I'm based. And so that really facilitated further collaboration after he arrived there. And so they are biological morphologists. So they are people who are, like all biologists, really interested in understanding evolution. And although they inform their work by the genetic results that are obtained by many of their colleagues, they themselves look at the morphology. And the reason for that is that although the genome is the mechanism for transmitting information from one generation to the next, the interplay between the environment and the individuals in a species one is studying happens through the bodies of the organisms one is looking at. So it remains important, even though we know how important genetics is, to also study the morphology and how that changes from one generation to the next under the under the pressure of environmental interaction with the organisms. So they study because they're interested not just in what happens now, but also in the past. And we typically have from the past fossils, mostly bones and teeth. So they study teeth and bones of both existing and extinct animals. Now that I've started showing you pictures, let me show you, I want to use the opportunity here to thank all the people I work with. So apart from Doug, there has been a whole gallery of people with whom I worked in early times and then more recently. And here you actually see where they all are, except Tingran is now in Chicago, and Roy has gone back to Israel. Shahar Kowalski is at University of North Carolina. Shanshan is now in Denmark. And in fact, when I was looking over my slides, I realized that I had lost a slide. So I don't have pictures for the more recent collaborators, Shira Fagenbaum, Solovin, Alex Wynn, and Ruik Sin. So it started with a discussion with the biologists. And at first, they gave us a very project where they were talking about the complexity of teeth. So what they were interested in, well, what Jukka Jönvall told me was that they recently had gotten a very nice result, and this is now over 15 years old, but on looking at molars of different mammals, and they saw that how complex this surface was correlated with the diet of the animals. And we're not talking about wear of the teeth. We're talking about really how complex the chewing surface was. And it gave great detail because it allowed them to see the difference between insectivores and carnivores, and in vegetarian animals between leaf eaters and fruit eaters and so on. And what was interesting was that it gave that regardless of the size. So once they had normalized the teeth to unit surface, it gave them that in comparisons that were valid for animals as small as a shrew, which is a very, very tiny insectivore, to animals as big as an elephant. And we asked them, well, how did they measure complexity of teeth? And it turned out that at that time, they were using a very indirect method. They were rendering the teeth. And when you rendered at that time, typically you would get an illumination, virtual illumination, by lights of different colors. And the different shadings that you would see in the two-dimensional rendering on your screen was interpreted by our visual system as 3D information. And so what they did in order to measure that was they would look at where colors changed in that two-dimensional display. And I said, so what you're really measuring is how the normal changes direction. And they said, yes. I said, well, we can define that mathematically. We can compute that mathematically. And that was the first thing we did. It was called DNE, for Dirichlet normal energy, because we were looking at that concept, the Dirichlet energy of the surface. And that led then to more interesting questions. That is something that I have noticed often in interdisciplinary collaborations, that a first question may not be very deep at the level of the mathematics and may link to mathematics we already know, although it's very rarely an off-the-shelf thing. And this was not off-the-shelf either. We still had to work quite a lot. And this was a project that Jarn Lipman did many years ago. But then you get more complex questions. And so that's when they came up with a question asking us, could we find an automatic way to compute distances between surfaces without landmarks? So let me tell you a little bit about the data they were going to give us. So since they work, most of the animals they work with, even though I've talked about elephants, they work mostly on much smaller animals. In particular, they work on lemurs and mouse lemurs. And so those have very small teeth. And so they are, the teeth are scanned via micro-CT. And then from that, a surface is constructed that gives in great detail the surface of the tooth. And from that, we do our analysis. Now, even though CT scans will give you spatial, three-dimensional information, voxels, we extract surfaces and only work with those surfaces because in quite a few cases, in almost all the fossil cases, Daubechies does not have the original tooth in his collection. He whenever he goes travels through the world to go to do field work or to go to conferences, he contacts all the local musea that have interesting fossils, and he makes 3D casts in very fine dental resin of their fossils. I mean, the actual specimens will not travel, but the casts he makes, he is entrusted with handling them, these precious fossils, and the casts he makes, he can take back. So we don't have anything of the original except that surface information. It is that still the resin is still micro CT scanned in order to get that detailed surface information, but only the surface is really important. So that's why we stick to surfaces. Now, what's typically done is that on these teeth, the experts will put landmarks. I mean, they know a lot about the evolution of teeth and the important features and so on. And so they typically when they want to do a study, they look at the collection of teeth in which they will study how evolutionary pressure, environmental pressure shaped the evolution of whatever feature they're interested in studying that time. They look at the collection they have assembled in order to do that study, and they identify homological points, so points that are similar, that they know are similar on all these different teeth, and they put landmarks on those. And once they have done that, they then use the spatial coordinates of these landmarks as the proxy for the information. So that's to say, they what they do is they represent that shape in R3K, and they then define so here you have such a collection that has been landmarked, and then they define distances by what they will do is they will look at how to take these K points in one sample and in another sample and find the best correspondence by Richard transformation, and then look at the sum of the squares of all those distances, and that will be their progressive distance squared. But of course, it's they wanted an alternative because they found, well, landmark placement is tedious and time consuming, and typically because it's time consuming, it's not done on the full collection. They do it on just enough points that they know they will have enough data to say something statistically significant. But there are many, many more in drawers in museums that could be used to get much more detailed studies, but that are not scanned because, well, landmark placement is tedious and time consuming. Also, in order to do this progressive distance, you need to have the same number of landmarks on each of the surfaces. So if you have a fossil that's missing a piece of tooth, that means that on that corresponding piece of tooth, you cannot put any landmarks on everything else. So you're losing the variability in that piece of the surface because you want to incorporate that one fossil that doesn't have any landmarks there. And you need a high degree of expertise to do this. So landmark placement can really be done only by people who really know the samples very well. If there were a way to do it more automatically, it might be possible for databases of bones or teeth or organs, for that matter, to be used by people who don't have expertise on that particular piece of the animal in order to test other theories they might formulate. And even in some cases, debates even exist among experts about where to put the landmark. So, as I said, the progressive distance, once you have landmarks, is done by taking the points on one of the teeth. So X and Y here now represent, I'm sorry, not X and Y coordinates and Z coordinates on one tooth, but the X's are for surface 1 and the Y's for surface 2. So you take the points on surface 1, you look at if you did a rigid transformation you apply that, you look at the surface, the corresponding point on surface 2, and you take the sum of the squares, and you take the minimized of all that sum of distances over all rigid transformations. And that's the procrustes distance. So what they wanted to do is, they asked us, could we find a distance that does as well for biological purpose as this procrustes distance? And could we do it automatically? Now, this is, I mean, not in mathematical terms a precise question, but what they had found was that when they approached mathematicians about distances between surfaces, mathematicians said, oh, we have many, many, many distances, and which are, I mean, not this procrustes distance, but they found that in general, those distances that were defined by mathematicians did not do as well for their purposes as this procrustes distance. So what they were saying was, we want something that really, for our biological studies, we know that procrustes distance as well. We'll do biological tests on what you propose us to see whether it has as much biological signal still as the procrustes distance does, or maybe more. So here's an enlargement to show you how finely discretized these surfaces are. So these things are typically in the tens of thousands of vertices. So we typically have to sparsify them to some extent, and because otherwise the data set becomes too large. So we defined in our initial study 2 different distances. So which we felt were inspired by what they proposed to us. And let me talk a little bit about both. The first is the conformal, so we call it the Wasserstein neighborhood distance. So in order to facilitate things, we flatten the surfaces. We do that via conformal flattening. Any 2D surface with a rim, which is what these chewing surfaces are, they're cut off at the transition between the tooth and the gum, so the exposed part of the tooth and the gum. So they are disc-like surfaces. You can conformally flatten them to discs, and you can keep the conformal factor. So that gives you a kind of landscape on the disc. And you can then try to see how similar points are on the disc, on one disc to point on the other disc. And what we do to do that is we look at little neighborhoods of each. And I should really have drawn them as circles, not centered on Z and W, but little hyperbolic circles there. I'm sorry to have been not so precise. And in order to compare them, because one thing we have to take into account is that when we flatten conformally, we're not doing we are not doing something unique. You can change the disk itself conformally to other forms of the disk by Möbius transformations. So we need to, if we define a similarity between points, to do that in a conformally invariant way. And one way we do that is by saying, let's define a conformally invariant way by taking this neighborhood and bringing it to the center, the other neighborhood also bringing it to the center. Now we have 2 little disks here, and we, of course, take the landscape, the conformal factor, so we have little maps on these 2 disks, and we can then compare them up to rotation. So we look at these 2 little landscapes on these recentered neighborhoods, and we look at how similar they are, and for each of the 2 conformal factor landscapes, and we minimize over rotations. That gives us this similarity between, depending on how we pick that radius. And then what we can do is we can do an optimal transport. So we do a Kantorovich distance, we take the minimum over all the all the measures on the product space that have the two mu and nu as marginals. And because our distance was conformally invariant, it doesn't matter which mu and nu we take. If either of them is changed by a Möbius transformation, our distance here is still going to be invariant under that. And we then implement and we get a distance. And we call that the conformal Wasserstein neighborhood distance. Okay. The other distance we defined was a continuous Procrustes distance. So remember, in the Procrustes distance, what we first had was a way of making points correspond. So let's assume that we have a way of making points on one surface correspond to another. And we define it mathematically as area preserving. And there's absolutely no biological reason to presume that it's area preserving. However, in practice, the way we're going to implement this numerically is that we're going to take a number of points on one surface, a number of points on the other surface, and both, remember, have been normalized to area 1. And we want to sample reasonably. So sampling reasonably, you typically do by making sure that each point represents, none of the points is too close to one of the other points. One of the ways in which computer graphics people do this is what they call a furthest point sampling. So you talk with a point and you get another point and another point and so on. And so you try to choose them so that they spread out nicely. And what that typically means is that if you were to draw the Voronoi region on the surface of each point, it would represent, if you have endpoints, about 1/n of the surface. Well, that means that you are really taking them as representing that 1/n of the surface and trying to put in corresponding with another 1/n on the other side. That means that you're really looking at an area preserving or an approximation to an area preserving map. So we said, in order to make a mathematical definition, let's say that we look at area preserving diffeomorphisms. And then you again look at the minimum over all the rigid transformations. So let's illustrate that here in this example at the bottom. I have two curves and I've made a correspondence map. Then for that correspondence map, I can look at a better reorientation of one curve with respect to the next, and the sum of all these little black lines squared, the length of the little black line squared is smaller in the middle here than it was on the left. But in fact, there are correspondence maps for which it is much better. And this is an example. So another correspondence map would give us much better. So we also have to take the infimum over the class of maps we're looking at. And that's why we needed to define a class to be able to take an infimum. So this is a rigorous mathematical definition. And we know how to compute an approximation of it in practice by means of this sampling on the surface. And we can prove properties about it. And in fact, you can prove, which is very useful for us, that when this distance is small, that the minimizing area preserving diffeomorphism is actually very close to a conformal map. And because the area preserving diffeomorphisms are a very difficult space to search, but the conformal maps are not, we use that because we are going in the end be interested only in the cases where these distances are small. Remember, we're going to use them ultimately in a diffusion distance. I mean, well, we at the beginning we weren't, but we did tell always our biological colleagues, but they didn't quite believe us, that only small distances were trustworthy. Okay, so this is the continuous Procrustes distance. And because it comes also with a map that goes from one surface to the other. Okay, so what we did is we had these two different surfaces. And in order to find how successful they were, we had agreed ahead of time with our biological colleagues that we would compare the distances in this kind of display, in which on the one hand we would show the distances for observer determined landmark placement and our distances. So the distances in both cases are symmetric, and we use the lower half of one symmetric matrix and compare it with the upper half of the other matrix. And we numbered the samples, were a little over 100 here, so that things that had a close distance were closer in numbers, which means that we were especially interested in what happened near the diagonal. And although the conformal Wasserstein neighborhood distance was so nice mathematically, it didn't do as well in reality. You see in these two squares near the diagonal, the computer continuous progressive distance did much better. We also looked at how the mappings would transport landmarks, and they did pretty well. So here are the propagated landmarks on 3 examples. And we were asked by the reviewer of that paper to look at things much more general than these. So we looked at talus bones and also the end of, I believe it was a humerus, but indeed, we did well on these biological criteria. Now, the interesting thing is that we indeed had bypassed explicit feature extraction. We had these mappings. And a funny thing happened after we had worked with our, I mean, in the year that followed, our biological collaborators really started looking at those maps much more carefully. I said, oh, look, we don't like that map and so on. And it became clear to us that although the question they had asked us was one about distances, once they saw we were defining mappings, it was clear that the mappings were of much more interest to them. They didn't articulate that, and it took me more than a year to twig of the discussions that wouldn't go anywhere. And once we realized that, we started working more on the mappings. Okay, now you've seen the continuous progressive distance is the ones that we were starting to work with, that they liked best, and it gave us with multidimensional scaling this grouping of 50 molars that are in groups of 5 genera, each genus represented by 10 species. So each genus has 1 color here, and they liked the clustering we had on the left. And when we then applied the diffusion distance ID to it, just to the same data that gave rise to this multidimensional scaling, we got the picture on the right. So now you have seen the problem in which I showed you this graph once before, but now you've seen the background about which we're talking. And we explained that this was a picture we obtained by taking small distances much more seriously than large distances. And as I told you, this was when our biological colleagues believed it. But in fact, we will do much better, and this was the essence of the PhD thesis of Tingran Gao. He designed a framework in which we went from the picture on the left to the one on the right. Let me tell you how he did that. So when we looked at diffusion distances, we lose the local distances, we knitted them together, we found a spectral parametrization of the data set, and from that we defined the diffusion distance. And so here I have a collection of teeth, and I had all these mappings from one to the other, and I used that to define this distance. And that's what we then use diffusion on. But the mappings in this picture were used only to obtain the numerical values for the local distances. But the mappings, of course, have much more information. So why throw them away? Why not keep them? And if you think of it, this picture here, if you think that the structure that we don't know, the one in which each of these teeth are a point on some structure, in which there is continuous variation possible, so maybe a manifold. So if we have this manifold, this underlying manifold, then each point is a surface. So each point is attached to another manifold. And we have mappings between all those manifolds attached to each point. So we really have a fiber bundle. It's a different fiber bundle than from what many geometers look at, because they typically like to look at spaces or a very geometric subsets of space of linear spaces, and it's not our case. But it nevertheless corresponds to a definition of a fiber bundle. So, and a fiber bundle is something where you have an underlying manifold, and to each point on that base manifold, a whole fiber is attached. And you have even mappings between those fibers. So that's called a connection. Okay, so we have these families of mappings between fibers, which of course, in our case, are going to be very, very noisy because we work with data. So we know if there's truly an underlying geometric connection, the picture we have of it through our computations is very noisy. And so he said, let's look on this higher dimensional subject and look at the diffusion on this fiber bundle, so where each point has both a label on the base manifold and on the fiber, and project at a much later stage to find the base manifold. Okay, so a few slides about to remind you of fiber bundles. So in a fiber bundle, you have a base manifold, you have a fiber manifold, you have a total manifold, so which would be the collection of all these points, and you have a way of, in the total manifold, of finding the base each point. So you have a map from the total bundle to the manifold to the base, the bundle projection. And you also want that it's locally trivial, meaning like here in this Möbius band, each locally, the structure of the total manifold is just a little interval times an interval, but globally, of course, it can be very different. Okay, so here are examples of bundles that geometers like to look at. Here, for instance, we are looking at the tangent bundle, where at each point on the circle we look at the tangent line to it, and we can limit that to a certain length as done here, or we can look here for this sphere at the unit tangent bundle. I mean, all the things that are on the tangent plane at each point, but that are at distance 1. Or here we have a different, this is not a different bundle again. Our bundle, of course, is more complex and less linear. But so we have this correspondence that gives us the mappings that we have between the fibers are, in a sense, give us an idea of the mapping that happens on the base manifold. And so what Ingrid did was he said, let me take all these teeth, let me take a diffusion on the entire bundle. Now, of course, then you have to, how do you do that diffusion? Remember, you have to build this enormous matrix. So within each tooth, the diffusion on the fiber is easy. I mean, we have Laplace-Beltrami, we know how to do that. Between teeth, we also have our continuous procrusted distance. We know it's only an approximation, but we can use that as an approximation for hopping from one tooth to the other in diffusion. And if you do that, so you have to set two parameters. Remember, we had to set a tau parameter for diffusion. So we have to set a tau parameter on the fiber and one between, because we don't know how to sync these others. So we have to explore that parameter space. But you can then find eigenvectors for that diffusion operator. And this is what I'm showing here. And so one thing you can do is, in that enormous space, you can already try to cluster. So let's say if you cluster, this is a clustering that Ingrid did, and on his 50 teeth, he then, for each cluster, colored the corresponding point a different color if it belonged to a different cluster. Already something that is striking, and it was not clear that this would be the case, is that each cluster is represented on each of the teeth. we have, I think it was 13 zones here, 13 zones on each tooth. And they're not in equal area. I mean, if you look, for instance, at, I don't know, this blue area in the middle here, it's clear that it's much smaller on some teeth than on others. So this was something that our biological colleagues really liked. They also really liked the correspondences. And in fact, they started using some of this straight away in one of their papers. We said, wait, but they never want to wait. As soon as there's something quantitative that makes sense, they already want to see what it will give on studies they're interested in. Tingran also proposed a way to embed the base manifold. And one way he did that was he said, let's take in all these eigenvectors, the points, just a piece of the vector that is corresponding to one of the teeth and look at its gram matrix and do that for each one of them. Note, and this is shown here as well, this is a situation where we don't need the same number of points on all the teeth. There would be no problem at all to also look at teeth that have a piece missing or that are not at the same resolution as the others. Okay, so one way you can do is doing what Tingran was doing, looking at these lower dimensional representations by looking at these gram matrices. Of course, a thing that you can do is just project to define a horizontal distance as the distance between the corresponding point clouds in k-dimensional space. In any case, you get distances that are much smaller, that are back to the number of different teeth you're looking at, and then you can use those in a diffusion picture, and that's what you get with this horizontal diffusion. So you first diffused on the full thing and then extracted the geometry on the base manifold from that, and we got much better separation. In fact, it's such a good separation that it contains more biological signal than before. It doesn't contain the species evolution. Well, we're only looking at their molars. For instance, blue and purple get clustered together, even though they are the furthest in relational, in evolutionary distance from each other. However, they are both frugivores, and the foliovores, the leaf eaters, are together as well, and the insectivore is separate. So it had a lot of biological signal. Now let me do a little detour. We believe that this fiber bundle learning method applies much more generally. I've done it here for teeth, but let me flash by a few. We tried it on digits of the database, the NIST database of handwritten digits, 1s and 6s. And we looked at, we defined maps from each to each, so that we would have this connection. And then we liked to cluster. Here is what you would get if you just do the standard clustering. And here's what you get if you use our fiber method for a number of 1s and 6s. So we feel that it gives a better clustering, a better separation. Here's a different groups of 1s and 6s. Here we did it for 4 digits. And again, although we haven't quantified it here, we believe it gives a better clustering. Okay, back to teeth. So this was just to entice you to take the picture series, the whole diffusion, horizontal diffusion, the bundle diffusion seriously. Okay, we can use the bundle eigenvectors to improve on our correspondence maps, and this is actually something I'm very excited about. If you take the top 3 eigenvectors, and here we use an embedding in which we make sure that the ratio of the different constants is such that the top three eigenvectors mostly talk about the diffusion on the fiber, but of course they do link things together via the connection. Then you get that each of the teeth has a representation in 3 space because we have 3 coordinates. And so each of the points gives us a kind of Pringle picture. And those Pringles very much look like they're describing the same surface. But of course, the points that we picked everywhere were subsamplings of these 30,000 points that were given to us. And the subsamplings, there's no guarantee that when we subsample, a point here corresponds to an exact point there. And indeed, on this Pringle, in this Pringle picture, we see that red and blue points don't correspond. But what we can do is we can look at one blue point and say, oh, what are the 3 nearest red points? Or the red points in the interior triangle of which we fall and that are nearby. Then we can find its barycentric coordinates, and we can say for that blue point, what is on the red side the equivalent, the barycentric combination of the corresponding red points, and that gives us a candidate for a better correspondence map. So we can do that. And in fact, here is an example of 2 teeth where I put correspondence. I show you some correspondences. Well, actually, this picture is a better picture. I show you correspondences, and I show you where they are moved as a result of the. So what I find is that the old point was there, but it gets moved to a better place. And when we show such re-registrations to our biological collaborators, they agree that these correspondences by and large make better sense. We are still in the process of quantifying that. But so we are very excited about this. We also want to use a local geometry adapted version of the procrustes distance. We have, so the DNE that we had originally turned out to be, to have limitations in its implementation, and a better version, a more robust implementation of the DNE, Ariadne, was written by Shanshan and can be used on many things. I mean, so here it's on a mollusk, here it's on teeth, and here it's on, I forget what it is, whatever, probably a talus bone, but I'm not sure. And she can fine tune the distance that she can take, and it is extremely robust to noise, much more than the old DNE. And so what we can do is we can, in our correspondence maps, instead of looking at just the local geometry, we can try to give weight to features, ridges, and cusps that are more meaningful to our biological collaborators, and that way steer the maps to build correspondences. We are also, and that's the very last thing that I'm going to talk about, to mention, because we're nowhere there yet. We want to explore the use of varying the rates of diffusion between the fiber and the base. So if we make the diffusion times on the base larger than on the fiber, what that means is that we are not looking at fine detail on the base, and we're really learning the fibers. So we want to use that in order to learn the fibers very finely. Once we have learned the fibers and improved our correspondence maps by the method that I showed you, we want to then change the relative weight of these 2 times, so that on the one hand, we look at things much more locally in the base, and start learning more geometry of the base after having improved on the correspondence maps. But that is work in progress, and I have no slides to show about that. So that's the end of my talk, I think. If I go down, yes, indeed.
Thank you very much, Ingrid. So at this point, we can take some questions from the audience. So if you have a question to ask, please feel free to unmute yourself and ask. So I have a question, if I may. Okay. So I was naturally thinking that, so if you were to, I mean, here you have a prior that the data comes from, or at least can be described by a manifold, perhaps a smooth manifold, whereas in evolutionary terms, and especially if you look at across kind of cross species, then the data may come from, it may also have a tree structure, maybe come from a fractal, but a combination of both, perhaps. So are these methods adaptable to such geometries? Actually,
you're absolutely right that, in fact, in reality, saying that it's a manifold is not really reasonable. I mean, so actually, I have a slide here that I can show. Here on the left are teeth of primates. And indeed, you could imagine that those are characterized by something that has smoothly varying parameters. But within the mammals, you also have, on the right here, are the teeth of a crab-eating seal, which actually doesn't eat crabs at all. It eats phytoplankton. But so, I mean, it's hard to see how you could have a smooth map that goes from surfaces on the right to the left. And we don't expect such a map. So for the moment, we're comparing species that are fairly closely related, and so that have a common ancestor not too far in the past. And although the relationship is via a tree, we believe that enough features are conserved that this manifold approximation for the full collection makes some sense. Mm-hmm. What we also believe is that, and that's something else, and I don't know how to do that yet, is that, and we want to inform that by the evolutionary tree, is that we have to do a multi-resolution way of doing this correspondence. And we want to look at the tree to identify how to sparsify, how to collapse certain features, so that at a deeper level, we still have a correspondence. If you think of the common ancestor, and if you believe there's a way of mapping via intermediate steps the surface.
That's right.
Might not be a correspondence between things, but if you go back to the common denominator in surface terms, then you would have that. So the idea is to, from the data, extract this sparsification at the level of the characterization of the fibers, so that each fiber has a multi-resolution way, multi-resolution representation, but that is informed not just by geometry, but also by evolution, and that we find correspondences at that coarser level, because it's the only level on which we have information in the stages that are further back.
Absolutely. Yeah, that's, I guess there's a lot to be done there.
Yes.
Yes.
And we can use help.
Okay. So any other questions, or we can, if there are none, I can stop the recording and we can still chat.
I have a layman question. Like, I don't know this area very well, but I am interested in topological data analysis. And some of the things that you talked about resembles me, things we discussed there. So when you get the data points, you have some topological features that comes from these data points by taking these weighted strips, complexes, and so on. So when you do this transformation to get this clustering, any of these features also still stays there, or do you lose all these features that will come from that?
Although I have I have a distant exposure to topological data analysis and RIPS complexes and so on from having gone to talks. I know too little, and I have not tried it because it's not an area that I know sufficiently well on this. I know a collaborator, Sayan Mukherjee, who's worked much more on them, studied some of these data with those tools, and I don't know of any results he obtained. What I feel, and I think it is also a question that would be wonderful to explore. I feel that both, at least some of the ways in which topological data analysis is done, in which you look at increasing neighborhoods and the topological features of the union of all these balls around data points, for instance, how they change as you increase the ratio of those balls. With diffusion, we're also looking at balls and how they change with our diffusion constant. And we look at properties of that whole complex. We just use different tools. In one case, you look at the union of all these and holes and how they persist as you change the ratio of the balls. In the other, you look at the spectral parameterization you get. It seems to me it should be possible to find a tool that unites both ways of looking at it, and that probably would do more than each of them separately. And that's something I've been trying to convince people to look at, but so far not with any success. I also haven't done it myself either. But I agree with you that
just something worried me was that the distances changed so much, like the clusters or certain areas. It was so like you change the distances quite a bit. I wonder if that kills some of these things that you catch with topological.
I don't know. I mean, what I show is just one way of visualizing what we find in our representation, our spectral representation. We don't throw away all the rest. It's just in order to show something. I try to look at 3D representations to show that distance relationship. But
thank you for your answer.
I don't hear you, Sinat.